Hello everyone, welcome back to Yadvian Talks. Today we are starting an important topic from Geotechnical Earthquake Engineering, that is Soil Dynamics and Seismic Design. This topic connects the theory to the real world engineering practice, and here we are going to see detailed overview of entire this context. Earthquake. What is earthquake? So the first question comes, what is earthquake? It is a shaking of ground caused by the sudden release of huge energy in the earth crust, and this energy creates a seismic wave that travel through ground, causing vibration that we feel. Types of earthquake. So there are four types of earthquake: tectonic earthquake, volcanic earthquake, collapse earthquake, explosion earthquake. So this is a small overview of earth section. So you can see this is a core, this is outer core. The inner core is made up of solid nickel and iron, and the outer core is liquid metal. Above we can see the mantle. Mantle is classified into two zones: lower mantle, upper mantle. And just above the mantle there is a crust which is made up of rock. So the crust is very thin at ocean and very thick at continents and the land. So the thickness of the crust is varies from 0 to 100 kilometers. So this is active geology of earth where all tectonic plate moves, and you can see each and every tectonic plate push and slide and collide with each other. So here one thing that animation is there, we can see when the fault happen at very deeper depth. Due to that fault crack into the rock, it emits the huge energy, and that energy travels in the form of waves and reach to just above the focus, that is called epicenter. And for the epicenter, this surface wave travels, which cause major most of the destruction. Now, the real world earthquake, how it is devastating earthquake we have depicted in history. Indo-Nepal recent earthquake in 2015, Myanmar earthquake, the entire construction of the building get collapsed. Taiwan earthquake, we can see the tilting and of the building and liquefaction so many places. Japan, we know 2011 earthquake which causes the tsunami. The recent Turkey earthquake which creates the huge amount of disaster in that country, which caused the landslide in Peru. So, what is a ring of fire? So, ring of fire is a 40,000 kilometer horseshoe shaped belt around the Pacific Ocean. You can see in this animation video. This ring of fire accounts for 90% of world's earthquake and 75% of its active volcano due to tectonic plate movement. So this is a very active geology around the ring of fire. So this is one animation which depict entire uh, magnitude of earthquake which occur all together this ring of fire. So the maximum earthquake comes in this area near to the Japan and in the Indian continent subcontinent. So who study the earthquake? Seismologist, a geotechnical engineer, and policymakers. So seismologists, what they do, they study the geology, seismic events, ground motion. Then the geotechnical engineering engineers get the ground motion. They make site specific seismic assessment. They do probabilistic and deterministic seismic hazard analysis. They create a model, FEM model, of the soil structure interaction. And finally, they conclude and recommend the seismic proof structure. The study of the consequences of Earth and the social economical impact is done by the policymakers so that they can make a better disaster management plan. This is seismogram you can see in the screen. which record the movement of the ground in horizontal direction and in vertical direction. Geotechnical engineer takes the ground motion, they convert into model, they study the model, and they run the FEM analysis to check the feasibility of foundation recommendation. And after that, policymakers they act on the prevention, mitigation, and preparation to account any disaster. Once the earthquake hits, so the major target of the policymakers to rescue and relief, to rehabilitate the population, and the reconstruct the destruction. Seismic waves. So, what is seismic waves? Seismic waves are vibration that travel through Earth, carrying energy released during the earthquake. They are categorized on where they travel and how they move the ground. So, based on this, it is categorized into two categories. One is body wave and surface wave. So, the earthquake begins at focus, release the energy as body wave. It comprises of two waves, fast P wave, that is called compressional wave, and followed by the slower S wave, that is shear wave. Once this energy hits the surface, it transforms into surface wave, that is love wave and Rayleigh wave, where the love wave is very dangerous one. While slower, the surface wave having higher amplitude and create an intense rolling and swaying motion responsible for the most structural damage and the building get collapse. So this is animation of the wave, how P wave compress the material and just transmit the energy from one point to other point. S wave shear off the material and transmit the energy from one point to other point. Surface wave just it twist and turn and make it rolling around and it transmit the wave energy from the surface. So this is body wave and this is surface wave. In the body wave, compressional wave is called P wave, shear wave is called S wave. In the surface wave, this is L shape. Movement of the ground surface is called L wave, and there is a Rayleigh wave. When you are in the swimming pool and the swimming pool wave, the wave of water comes, so you feel a motion up and down. That is called Rayleigh motion. Seismogram. What is seismogram? Seismogram is a visual device which records the ground motion and produces the seismograph. It displays the arrival of different seismic wave over the time. Traditionally recorded a ink line on the paper drum. So modern version is digital graphs showing the time on x-axis and an amplitude of vibration on y-axis. Now this is a seismogram, typical seismogram. You can see in the starting of when time is 0 and as the time elapses there is a background noise, and after that the P wave arrives first, and after the P wave shear wave arrives, and then we record the surface wave. So P wave is quite faster. So the time interval between P wave, arrival of P wave and arrival of S wave, and that is called time of arrival of first waves, right? So this is a graphical representation, right? So this is a graph of P wave and this is graph of S wave. Now each and every time we can depict d1, d2, d3. This is the distance between the epicenters, right? So now here we are going to see how we calculate the epicenter of the earthquake. So this is center of seismogram 1, this is the d1, and around it we place one circle. This is the second seismogram d2, and we place a circle around d2. Then seismogram 3 and distance is d3. So this d1, d2, d3 is the distance which is calculated from interval between the S wave and P wave. And the conjunction point here where all three circles meet, is called epicenter of earthquake. The magnitude. You often heard about magnitude. What is magnitude? So magnitude is a measure of total energy released at earthquake source, calculated from seismograph data. So it is measured in two scales, Richter scale. So it was developed in 1935, the first widely used method. It is based on amplitude of the largest wave recorded. So the equation is given here. And second, how to calculate the magnitude is the moment magnitude scale, MW. And this is widely used method. The moment magnitude scale measures the total energy released by earthquake, and this is most reliable scale for the smaller one and the larger one. And this is formula for it. So we are going to see how to calculate the magnitude. So this is two example that we are going to discuss, where the amplitude, maximum amplitude is 23 mm, the epicentral distance is 100 kilometer, and distance correction is 10. Because this is the formula to calculate the Richter magnitude. So we put all these three value and we'll get the magnitude of earthquake, which is 4.4. Now we will calculate the seismic moment and moment magnitude, right? So seismic moment is denoted by m0, which is equal to mu ad. So the rigidity of rock is very important here, 3 into 10 raised to power 11 dyne per centimeter square. Fault length we will required, fault width we will required, and average slip depth we required. So we convert all the unit into same SI unit or any recommended centimeter unit. Next, calculate the fault area. Next, calculate the seismic moment. Next, moment magnitude. So here we get the moment 10. So this is one method to calculate moment magnitude of earthquake. So often you have heard about the intensity. What is intensity? Intensity, it can be referred to two different things: observable damage and design force level. So which is called seismic zone factor. For an engineer to design the structure, they require design force level, right? Seismic zone factor. So observable intensity, basically it is called modified Macaulay scale. So this is one table where intensity is depicted in 1, 4 and going toward 12, right? So not fell, moderate, strong, destructive, and catastrophe all together. All this level of destruction which can we observe is given here. Based on the physical observation, we can put intensity here. So design intensity is a very important thing for engineers. Somehow we cannot design based on magnitude 7 or intensity 11, right, or 10. But instead of these things, all standard codes for the designing these structures require, and they divided their country into different regions, seismic zones, each zone having zone factor, right? What zone factor is nothing but the peak ground acceleration value for that specific area of the country. So we'll see the seismic zone. What is seismic zone? This is the global map of seismic hazard, where the red color shows very intensive earthquake will come with higher peak ground acceleration. This is a map of USA, where you can see in the east coast it is a very higher chance of getting earthquake with higher magnitudes and PGA. This is Europe seismic zone, and this is seismic zone of India based on 2016, where we divided India into four category: zone 2, zone 3, zone 4, zone 5. All Himalayan region is based on zone 5. So seismic zone of India, it is now revised in 2025. Before, in 2016, there is one code, IS 1893 2016. Now, in 2016, there is only 4 zones, but in 2025, there is 5 zone, one extra zone they added. Now, the maximum zone factor was 0.36, but in 2025 it is updated to zero point 0.6 pga. So what does this mean, 0.36? So very clear. So this is 0.36. We usually call it g, right? So in terms of g, so this is 9.81 meter per second square acceleration due to gravity. So we'll multiply by approximately 10. So the acceleration due to gravity is for the earthquake is 3.6 meter per second square. So this is modified seismic zone of India with added the zone 6.